Hello everyone. In this video, we are going to study linear regression, which is the simplest and the basic model of machine learning. We are going to study linear regression using normal equation in this video. So the agenda for the video is we will be studying the intuition behind linear regression, then we will derive the normal equation, and then we'll see what actually pros and cons of normal equations are. Because of that, we have to jump onto the next uh, type of method for basically optimize the model parameters in linear regression. So let's get started for this video. So first question, what is the linear regression actually means? Linear regression is a basic machine learning model, we can also say statistical model, used to build a relationship between a dependent variable and one or more independent variables. Now, if it is just about one dependent variable and one independent variable, then it is called as linear regression. And if it is like one dependent variable and one more than one independent variable, then it is known as multilinear regression. Okay, so in this video we are just gonna stick to linear regression, that is single point linear regression. Okay, one to one. So we can also see the graph I have given below. So in this we just have to find the best fit line that minimizes the error between actual and predicted values. So now I will show you what actually means by actual and predicted values. Okay, so in this particular graph we can see that there are some blue dots and one whole red line, and we have given two parameters, that means two variables. First is umbrellas sold, how much umbrellas are sold, and second parameter is rainfall. Okay, so in this particular graph we are going to study that how the sell of umbrella is dependent on the amount of rainfall happened, the amount of rainfall took place. Okay, so basically these data points are collected by the data surveys that is done by companies and all. So we got this data and then we plotted it on this particular graph, and then we just plotted one fit line that one line that fits all these data points, like maximum data points. So what do you mean by fit the maximum data points? So we will see now. Okay, so suppose is there any data point over here? We will go through graph. Okay, let's see here, it is like 0.131 point something is there, like this much amount of rainfall took place. Okay, now we have our one data point over here. And what actually the line predicts, we can see it here. Just have to rub it. Just draw a straight line, you will find it. Yes, so this is basically what we can say, 40 units of umbrellas are sold. Okay, when the rainfall was 131 mm. Okay, and If we rub all these things, then you can see here there was a data point, this one, that was actual data point, like we have surveyed it and it is registered in the records. And this one is found through the line, this 40. And this is what, can just rub it and draw it a little bit clearer. Okay, so here is the actual y output, we can say. So let's suppose this is 35. Okay, this point is 35. So what you can say, that 35 is basically the actual value, the actual value of how much umbrellas got sold. Okay, and 40 is the predicted value, predicted by what? Using linear regression model, we have drawn this line which fits these particular data points, and then we have found that at this point of time we have this much umbrellas sold. Okay, right? You got this. Yes. So we've got our predicted value and actual value. 40 is what? Our predicted value, predicted by linear regression model, and 35 is what? Our actual value that we got from data survey. Okay. So the best fit line is which minimizes the error between actual and predicted values. Now what is the error? Error is basically the difference between the actual and predicted value. Okay, here what is the difference? 40 minus 35, we can say the difference is 5. What is the difference? The difference is 5 units. Okay, so this is basically the error between our prediction and the actual value that was supposed to be correct. Okay, so I am pretty sure that you got the point of what actually the predicted and actual value means in this particular graph, and what does the best fit line means by intuition. Okay, so let's move on to the next slide. Now we will see the intuition behind linear regression. See, the models are just not about, graphs, and just not about to implement it using a programming language. It is about how you can relate it with real life analogy, and you can understand it, that how can mathematics predict what we are going to achieve, what outcomes we are going to have. So this is very important to study everything in machine learning with intuition. Okay, so let's see what is the intuition behind linear regression. The goal of linear regression is to find the best fit line. Just I have said it earlier only, that we have to find the best fit line where all the data points that we've got from the surveys should be uh, very close to that point. So that is what it means by best fit line. Okay, so that models the relationship between input variables and output variables. So basically it models, it shapes the the relationship between the input features and the outcome we are gonna have. So this is what basically is the goal of linear regression. Okay, this line helps us in predicting future values accurately. Just I have said it earlier that we have built the model, we have built the graph, we have the predicted line that is best fit for it. Okay, so if anyone gave us like a particular rainfall parameter or rainfall data, that this much amount of rainfall happened, this much amount of rainfall took place, so I just want to predict how much umbrellas are gonna be sold. Okay, so that is what basically we are predicting here. We are predicting the future values. We don't have actually the idea that that amount of rainfall is going to take place, but we are we can predict it with the help of linear regression, with the help of help of that particular best fit line. Okay, now there is there are two basic things we have to keep in mind when we are going to study, like we are going to study linear regression. So these two are the basic things. Okay, the best fit line minimizes the overall difference between the actual data points and predicted value. Just I have said earlier that best fit line means the line that is actually close to the actual data points, right, that we have got from the survey. So what it actually does, it minimizes the overall difference between the actual value and predicted value, so that we find the best fit line. So that is basically what linear regression is, and it represents the trend of data. Trend of data means, just like we have studied like the past, from the past data points we can predict the future ones. That is basically the trend going on, so we go with the trend, just like going with the flow. So that is basically what linear regression represents. It represents the trend of data. So we are going to we are being able to find what actually um, the outcome gonna be for the particular amount of rainfall which can be taken place at any point of time. So that is what the trend of data means. Let's move on to the next slide. Mathematical representation. Now let's come to the practical approach, like how actually the equations turn out into intuition and apparently turn out into the predictions. The equation of linear model is basically y is equal to xw plus b. Any student who have studied normal linear equation can just uh, understand this particular equation. But the key here is we have to go with intuition, not just by the formula. So here y is output target variable, x is input features, that is independent variable, w w is basically weights. We are going to see what w actually means, like with intuition, in next slide. And bias means it is an intercept term. Okay, now our task is to optimize the weight to find the best fit line. Okay, so our target is to reduce, to reduce the error, to reduce the difference between the maximum value, reduce the difference between the actual value and predicted value using the optimization of weights. So this is what our goal is. So let's move on to the next slide. Now let's come to the formula intuition. Now what is basically weights and biases? Think of it like predicting marks based on study hours. Okay, how much hours you studied, you can predict your marks by that. Like this is very hypothetical. Number of marks are actually not very proportional to the study hours, but for example we have taken it. Now Bias. What is bias? The bias is marks you get without studying at all. It actually means that you studied for 0 hours. Okay, let's see with a graph. We will build a graph over here. So this is y-axis, that is output, that is marks obtained. We will just short it out as m, and we have study hours on x-axis, and we've got this particular line. Okay, the line of this the equation of this line is y is equal to wx plus b. Now we've just read that the marks you get without studying at all is bias. Now marks we get without studying means what? Like we have studied for 0 hours and we've got some marks. So that is what bias is. Now intuitionally we can say bias is this, right? We can say this is bias, this length is our bias. When we have studied 0 hours, here we can consider it as origin. Yes, this is basically what bias is. When we have studied for 0 hours, then how much marks we got? So this is what basically bias is. It is the intercept. What we call it in maths term, it is an intercept. Okay. Now come to weight. Weight is the rate at which marks increase per extra hour of study. Per extra hour of study, the marks increase. Okay, the increase in marks when we like it is the rate at which marks increase as per we study extra hours. So by intuition we can say that it is the slope, you know, this, maybe this angle is theta. We can say slope is equal to as tan theta, right? So this is what W is, right? W is basically the slope that we got through the line. How much tilted is this line from the x-axis? That is what, from the positive x-axis, that is what slope is, and that is what we call as weight. Okay, so this is what the intuition of the formula is. This is how we predict. If we got some, data points over here like this, so we can say this is the best fit line. Why? Because we can now we can actually see that the data points are very closer to the line. Yes, so that the difference between the actual values and the predicted values is very less, and because of that it is the best fit line, right? So this is what the prediction, the intuition behind the formula of linear regression is, and this is how the prediction happens. This is how the prediction takes place in machine learning. We predict very small things, very basic things with just mathematical formula. So I think you got the intuition, formula intuition. Let's get to the next slide. Yes, now comes the crucial part of the whole PPT. Let's see what is loss function. Loss function or mean squared error function. Okay. Now MSE is basically it measures the average squared difference between actual and predicted values. It quantifies how well or our model fits the data. Now we can see, we know what the mean is, right? Loss function is basically the error, you know, the error between the actual values and predicted values. That is loss function, what loss we got from the difference of the predicted value and the actual value. And we use this error, this particular error function, that is mean squared error function, to optimize our linear regression model. Okay, so what is MSC? It is the average. Average means, here we can see the formula. Here n is the number of data points, yi is the actual value, you know, the actual outcome, and yi hat is basically our predicted value. Predicted using what? Predicted using basically the formula that we have seen earlier. Okay, right? So this is what MSC is. It averages the difference, the square of the difference between the actual and the predicted value. Just this is what MSC is. Okay, I think you got the mean squared error whole definition and what actually mean squared error is. It is the squared error. What do you mean by error? See, this is basically error without this 2. Okay, just forget this 2 for a second. This is what we called error, right? The actual value minus the predicted value. This is what we called error. So this is the error squared, squared error. So we just square it and then we summify it for n data points. We summify, we summify it for n data points, and then we will just average it. This is what mean squared error is. This is mean. This is, from this we get the mean, from this we get the error, from this we get the squared error, and the whole formula we get the mean squared error, which is our loss function, which will be helping us further to optimize our model parameters, are to just find the best line for prediction. So let's move on to the next slide. Now let's see the MSC intuition. Why we minimize squared errors. Squaring the errors ensures all errors contribute positively. Now at this point of time, I think you all guys know that negative error doesn't make any sense, right? Error should be always positive. Like error is basically what? The mod, the mod between the mod of the actual value minus the predicted value. It is the mod. it is the mod, right? Why? Because the negative, the negative error doesn't make any sense. So that is why we, squared errors contribute much in the MSC mean squared error, so that we can find the best fit line, because mean squared error by differentiating mean square error, we will see it later on. Differentiating mean squared error function, we will get the optimized model parameter, and from optimized model parameter we can get our actual best fit line of linear regression model. Yes. Now maybe one question you guys will ask me, that why don't you use this particular formula, that yi minus yi hat mod of this is also positive, then why we have to use squared errors, right? The answer of this particular question is in this point. Large errors are penalized more than small errors. See, what do you mean by large errors? Large error means the actual data point is very far from the best fit line, right? Now, if we want to find the next best fit line, if we want to optimize the model, then we have to minimize this error, and for that we have to minimize the large errors more than the small ones, right? For particularly for that reason, we have to use the squared error function over here. We don't we can use this one, but this one will not give us the optimized model parameter. Why? Because the large error will have the um, most impact on the model, right? Small errors will not exist anymore. If we have, just like if we add up infinity plus 0, okay, then it will actually tend to infinity, right? Or let's say we will take the next example. For example, we add, like, 11937. Now we are adding 1 by 2, like zero point 0.5 in this particular number, then we can approximately say that it is equal to 11937, right? Why we can say that? Because as compared to, in this we are doing a comparative study, not really numerical mathematics, right? This particular thing, this particular number is much bigger than zero point 0.5, right? And that is why, by intuition, and by for minimizing the error and predicting the rough value, we can say that this is equal to this, right? Like that only, small ones, like, the small errors don't contribute much in the error function, but the large errors did do large error do contribute in the error function, and that is why we need to penalize the errors to basically find the best model parameter, and that is why we square it. We could have used the mod only if this makes sense. That doesn't make any sense, but just for this particular reason, that large errors are penalized more as compared to the small ones. So this is why we use square, right? Now come to the next point. MSE provides a smooth and differentiable function, making it easier to optimize. Now, we can say in previous slide, we saw that MSE is basically quadratic function, right? It is a quadratic function. Let me erase all this. It is a quadratic function. How we got to know that it is a quadratic function? It's squared, right? So every squared function is a quadratic function. So if we draw a graph of any quadratic function, it comes basically like this. We've got the global minimum, we've got the local minimum. In this particular thing, in this particular squared error function, we get the global minimum and the local minimum at one point. We don't get like if we have order 3, then the graph could be like this. Here we have two minimums. Why we are talking about minimums? Again, because we have to optimize the error function, and in order to optimize the error function we have to differentiate it and make it zero, right? We have to find the minimum. We have to find the minimum squared error function. We have to find the minimum squared error where it is it exists, and for that we have to optimize this particular, we have to differentiate this particular function, and we'll get the optimized model parameter. So if we use like higher order things, then our local and global minimum is different, and that is why it is hard to judge. Like if we got this one, okay, this is not the minimum, right? This is the minimum, this is the minimum here. At this point of time we get the least amount of mean squared error. So if we got this, like by differentiating, then we cannot say that this is the best model parameter for the linear regression model, right? So that is why the quadratic function is the best type of function to use in optimization thing. So I think you got these two 3 points. So let's move on to the next slide. Now, as we've discussed it earlier, the goal of the linear regression. Goal of linear regression is basically we find the optimal parameter, and that too by minimizing the mean squared error, ensuring our predictions are as close as possible to the actual values. This is what we are gonna do, right? If we want to find the, if we want to find the best fit line for our linear regression model, then we have to optimize the parameters. And how can we optimize the parameters? By minimizing the error, right? And for minimizing the error we have to take help, we have to take help from our some of our mathematical tools like differentiation. So let's get in there. Now, there are two methods to minimize MSE. The two methods are normal equation and gradient descent. Okay. In this video, we are just going to see normal equation. In the next video, we are going to implement the normal equation in Google Collaborate. Okay. So yes, let's go with the normal equation now. Introducing the normal equation. Now don't get confused by this particular theta. This is W. This is our model parameter, that is weights. Okay, we have to find we just have to find the best value for W, right? This is our model parameter. Parameter of our model, that is model parameter. right? Now don't get confused or don't get, scared by this formula. I will explain it now only. Now this is what normal equation looks like. We found the best fit model parameter to find the best fit line for our linear regression, right? Now the x is same as input features, and the y is also same as the output. This equation directly computes the optimal parameters w without iterative updates. Now what is iterative updates? Iterative updates is basically where we iterate things. Sorry. In the there is the second method to optimize the model parameter, that one, that is gradient descent. In that we iteratively optimize our model using learning rate, right? It comes from solving the derivative of MSE function with respect to w. Now, I've just said it earlier that we have to find the derivative of MSE function, and then we have to make it equal to 0, and then we will get our best fit model parameter to find our best fit line. Yes, so let's see how. Yes, here comes, don't be afraid of this derivation. This is pretty easy, right? Now I'll explain you actually what, actually step by step, what is happening here. Now this JW is basically, don't be get confused by cost function. Cost function is basically the loss function. I will explain the difference between cost function and loss function in the upcoming videos, but don't get confused for now. For the sake of this particular derivation, just keep this in mind that this is the loss function. Okay, this is the loss function, which we are denoting by j of w. W will be the parameter over here. Now here 1 upon m is the data point. Okay, we've seen this formula earlier. This is MSE formula. Just here it is not y hat. It is basically y hat only. Here x and w are given in matrix format. Keep this in mind, okay? X and w are in matrix format, and that's why we are not taking the bias term over here, because it is constant and we are going to differentiate this. So anyways it is gonna be 0. So that is why we are not taking the bias term, okay? And here x and w are the matrix, are in the matrix form. Now this is basically the cost function, right? We will start with this particular cost function. Now we will convert it into matrix form, right? Just I have said. Now how they have written this. This is basically the transpose of this particular matrix. Transpose is, if you don't know much about matrix is basically like this. No? A, B, A, B. For example, I am taking this. This is 2 by 2 matrix, okay? 2 rows, 2 columns. This is 2 by 2 matrix. And a transpose of this particular matrix will be like this. A, A, and B, and B. Basically what we do in transpose of a matrix is we replace the rows by columns and columns by rows, right? Like this, okay? And when we multiply these two things, like the matrix to its actual transpose, then we get this, we get the square of the particular matrix, right? This is why we have written it like this. We have divided it into two parts, and we have written it right like this. I hope you got this. Now come to the next step. Compute the gradient of the cost function with respect to w. Now what is meant by gradient? We just have to differentiate the jw function. We have to differentiate the cost function in order to get in order to get the best model parameter. Now we will differentiate this. Now if you don't know matrix differentiation, let me take you through it. It's very easy. This basically, when we differentiate this particular thing will disappear, because anyways we are going to make this particular different derivative as 0. So the 1 by m, the constant term, even if it is here, it will be 0, right? Now 2 of x of t, we got this from here, right? And then we have differentiated this particular matrix, right? And then set the gradient to 0 to minimize the loss function. Now we have set this gradient to 0, and then we got this particular thing. When we calculate 2x x transpose into y minus x or x into w is equal to 0, then we get some equation like this. And then when we solve for w, we basically get this particular equation. So I don't know if you are able to see it or not. Yes. You can calculate this by your own also. Just try it for once. This derivation is not so hard. Just once you have to look into how you can derivate, you can find the derivation of matrix. Once you find it, then it will be very easier for you to find this particular formula. Okay. So let's move on to the, I think you got the derivation of the normal equation. It's very easy. Okay. So try it for once by your own, and you will get the whole scenario, how we got to the answer of the best, to find the best model parameter of the particular linear regression model. Okay. Now let's come to the advantages of normal equation. What are the advantages? We don't need to choose a learning rate. Okay, just like I've said it in the introduction slide of normal equation, that we don't have to iteratively find, we don't have to iteratively optimize to in order to get to the best model parameter in normal equation. Okay. And the next point is direct computation of rates. So in this we just have to derive the we just have to take the derivative of the particular MSC function, and then we will directly get the particular optimized the best fit model parameter from the derivation. Okay. And third point is works well when the dataset is small to the medium sized. Now this needs a comparison between the gradient descent optimized model and normal equation optimized model. So this point I will discuss in the gradient descent video also, but for the sake of time you can just remember that it works well with the data set, with the small data set, because if we have big data set, then the cost function the differentiation of cost function will be very computationally hard for us, and that is why uh, it works well on the small data set. Okay. And fourth point is avoids the need of iterative optimization. Obviously I've said it in the first point only, that in learning rate we have to when we use learning rate for optimization process, then we have to iteratively optimize the particular model. So in this particular method of normal equation we don't have to iteratively optimize. So this is the advantage in normal equation method. Now come to the limitations of normal equation. Limitations of normal equation, as I have said earlier, for larger data sets, the it is very complex. It is computationally expensive. When the complexity of the particular method is big O notation of n cube, so it is very complex. We have to iterate for three more loops, right? Even when we find the derivative, it is computationally expensive only, and here we are directly finding just one model parameter and in one go, so that is basically very computationally expensive. uh, the second part is requires matrix inversion, which may be unstable if x transpose into x is singular. Now what do you mean by singular? Singular means the the let me explain with the pen. Yeah. Now when the multiplication of these two matrices become zero, then it will be very hard for us to invert this matrix, because when we invert a matrix, then it is basically we have to divide 1 upon the value of the matrix, the determinant of the matrix. And if the determinant of the matrix is 0, singular means 0. Okay, this multiplication of these two matrices is 0. That means this particular multiplication is singular, this particular matrix comes singular. Okay, so inversion of this matrix will be very hard if this particular multiplication of two matrices is singular. So that is why it's unstable. Not feasible when number of features is very large. Number of features are obviously if the x we've given as the input variable, independent variable, if it is very large, then obviously it will become more computationally expensive again, and we won't able to find the best parameter model. It will be hard for us to do that. Now yes, the recap. Linear regression is used to model relationships between the variables, output variable and input variable. Second point is the mean squared error quantifies the error in predictions. The third point is the goal is to optimize MSC by optimizing parameters. We have to optimize MSC. What do you mean by optimizing MSC? Minimizing MSC, we have to um, minimize the difference between the actual value and the predicted value, so that we can find the best parameters for our model. The fourth point is normal equation provides a direct solution without iterations. Like there is no need to choose learning rate, and hence we don't have to iterate all the way through all the models, and then we have to find the best model parameter. So this is one advantage in normal equation. Works well for small data sets, but it is computationally expensive for large data sets. As we have seen earlier, the disadvantage of normal equation we have, it is very computationally expensive because of the big O notation complexity is like n to the power 3, and that is why it is best for small data sets, but large data sets, it's a big no. So we'll try to implement the normal equation in Google Colab. So it's like hands-on experience with Python programming. We will be implementing the normal equation in the next video. So thank you for watching, and I hope you understood all the points I have covered in this particular video. And if you find this video helpful, then please like, share and subscribe to the channel. And thank you for watching.